Hey guys, welcome to Exam Jam. These videos are all about helping you revise for your exams. This video is all about polar molecules and dipoles. But before we get down to that, there's a few things we need to know. So here's a quick roundup. Number 1. Electrons orbit the nucleus at certain energy levels called shells. These shells are made up of 4 different atomic orbitals, which all have different shapes. S has 1 orbital, P has 3 orbitals, D has 5 orbitals, and F has 7 orbitals. Each orbital can hold 2 electrons, which spin in opposite directions to each other. Number 2. The grouping of the same type of orbitals are called subshells. Each shell gains a new subshell as it moves away from the nucleus, and we can either write these down as shells, orbitals, and electrons, or draw them as electrons in boxes. Number 3. These subshells have different energy levels, which generally increase as you get further away from the nucleus. But there is always an exception to the rule, and in this case, it's that the 4s subshell is at a slightly lower energy level than the previous 3d subshell. Pretty annoying, but as long as you remember that, you're grand. Number 4. Filling the shells and subshells goes by a set of rules called the Aufbau principles, which state that electrons are added one at a time, the lower energy shells, or shells closer to the nucleus, must be filled first, and each energy level must be filled before a higher energy level starts to fill. Number 5. There are 3 main types of chemical bonds: ionic, which happens between a metallic and non-metallic element, covalent, which happens between 2 non-metallic elements, and metallic, which, you guessed it, happens between 2 metallic elements. If you need any more help with that stuff, let me know in the comments and I'll make some more in-depth videos about them. So now, let's talk about polar molecules. To understand polarity, we first need to look at electronegativity. So what is it? Electronegativity is the ability of an atom to attract the shared pair of electrons in a covalent bond, and is measured by the Pauling scale. As you go towards the top right of the periodic table, the electronegativity increases because there are more protons in the atom, but actually decreases as you go down the periodic table, because the increase in shells means the valence or outer electrons are shielded from the effects of the protons in the nucleus. This means that fluorine has the most electronegative atoms. Now, let's look at polar bonds. To have a polar covalent bond between 2 atoms, you need a difference in electronegativity between 0.5 and 1.6 on the Pauling scale. Anything more than that, and we've got an ionic bond. So let's look at the hydrogen molecule. Because the 2 hydrogens don't have a difference in electronegativity, the sharing pair of electrons are shared equally between the 2 atoms. Hydrogen chloride, on the other hand, is a different matter altogether. That's got a polar covalent bond. This is because the difference in electronegativity causes the chlorine atoms to pull the shared pair of electrons towards it. So hydrogen, which is losing this tug of war, gets a slightly more positive charge, and chlorine gets a slightly more negative charge. We can show this by using the Greek symbol delta. And we now end up with a molecule with 2 different charges, or poles if you like. In other words, we've got a dipole. So is electronegativity the only thing that makes a molecule polar? No, not quite. The molecule geometry also plays a massive role in determining whether the molecule is polar or not. Take carbon dioxide for example. The oxygen atoms are delta negative, which means they repel each other equally around the central carbon atom, giving the molecule a symmetrical linear shape. This means that although the bonds between the carbon and oxygen are polar, the molecule overall isn't. And this also applies to other symmetrical molecules, like tetrachloromethane, which has a 3D shape. Although the polar bonds between the carbon and chlorine are present, the dipoles are acting in different directions, so they cancel each other out. So what about polar molecules? They have a non-symmetrical structure, either because the electronegative atoms are hogging all the electrons, like in hydrogen chloride, or because the lone pair of electrons on the electronegative atoms are repelling the other atoms away, giving a bent geometry. This results in clear dipoles being formed on the molecule. The best molecule to study polarity is of course water. Water is amazing. It's what has allowed us to exist as a species. And thanks to the interactions of molecules, it's got some pretty cool properties, like surface tension, which allows pond skaters to skim over the surface of ponds. But how? It's all thanks to intermolecular forces, or the forces between the molecules. These forces occur because of the random movement of electrons in the shells of atoms bonded in a molecule. They don't involve sharing the electrons like in chemical bonds, so they're a lot weaker. There are two types of intermolecular force: hydrogen bonds and van der Waals forces. Remember, although hydrogen bond has the word bond in it, it's not actually like a chemical bond at all. And in fact, compared to a chemical bond, these forces are pretty small. A hydrogen bond is a strong permanent dipole interaction between an electron-deficient hydrogen on one molecule and a lone pair of electrons on another highly electronegative molecule. So in the case of water, this would be an interaction between the delta positive hydrogen and the delta negative oxygen. In ice, these molecules form an open lattice structure, and hydrogen bonds form between the ordered H and O molecules. This actually pushes the molecules apart, causing the ice to expand and become less dense. When the ice melts, the molecules get closer together and form shorter, fleeting hydrogen bonds with each other. And this is why ice floats. The strength of these hydrogen bonds also explains why the boiling point of water is higher than if these hydrogen bonds weren't present. The second type of intermolecular forces, van der Waals forces, are much weaker than hydrogen bonds and actually describe several types of intermolecular forces. These are 1. Permanent dipole-induced dipole interactions, 2. Permanent dipole interactions, and 3. Dispersion forces. These are a bit of a mouthful to say, but they're actually self-explanatory. So let's take the first one. A permanent dipole-induced dipole interaction happens between a polar molecule and a non-polar molecule. When the polar molecule, which has a delta negative side and a delta positive side, i.e. it's a permanent dipole, approaches a non-polar molecule, it causes the electrons in that non-polar molecule to shift slightly, either being repelled by the delta negative side or attracted to the delta positive side. This means that the non-polar molecule is now slightly polar, and the polar molecule has induced a dipole. Permanent dipole interactions happen between two polar molecules. Let's take hydrogen chloride for example. A delta positive hydrogen is attracted to the delta negative chlorine, a bit like magnets. Hydrogen bonds are a type of permanent dipole interaction. But not all permanent dipole interactions are hydrogen bonds. These two intermolecular forces are called permanent dipole forces because they involve at least one dipole. I've said dipole far too many times in that sentence. Last but not least, dispersion or London forces. These forces happen between two nonpolar molecules. But how? Well, electrons are constantly moving within shells, which means that at any point there could be a shift in charge because of the accumulation of electrons. This means an instantaneous dipole is formed and induces dipoles in neighbouring molecules and attracts them. These forces get stronger with increasing number of electrons, quite simply because there's more electrons to create a negative charge. And that is the end of our polar mission. I hope you found this video useful, and if there's any topics you'd like me to cover, leave your comment in the comments below. Or you can go check out my social media links and leave a tweet or a comment there. All the links are in the description box down there. If you found this video useful, give it a thumbs up and subscribe to my channel for more general and wacky science. Thanks for watching. Have a wonderful day.